I'll make a bet with you. Your bus comes every 10 minutes on average. You don't know the timetable, you just wander over to the stop whenever. How long do you wait on average? The answer that feels completely right, 5 minutes. Half of 10, obvious, and it's wrong. For buses that arrive at random, you don't wait 5 minutes on average, you wait the full 10, exactly as long as the entire gap between two buses, as if you showed up at the very start of a fresh gap, every single time. Sounds impossible, I know, but it's cleanly worked out and measured against real bus data. And as a bonus, it explains that nagging feeling that the bus always dawdles on the day you actually need it. This is the waiting time paradox. And the sneaky part isn't that 5 is a little off. The sneaky part is that 5 feels like a fact. 10 on average, I show up somewhere in the middle, so obviously half. The thought is so clean, so self-evident, that you never stop to check it. It's the kind of wrong answer only a good intuition could produce. And that's exactly where it fools you, right at the spot where you feel most certain. So let's be honest and start where your gut is actually right, because that case really does exist. Picture a bus that runs like clockwork, every 10 minutes, to the second, 8 o'clock, 8:10, 8:20, flawless, no traffic, no delay, drawn as a timeline, identical gaps, side by side, each exactly 10 minutes wide, like the teeth of a comb. Now you arrive. You don't know the schedule, so your arrival point lands completely at random on this line. Sometimes just before a bus, sometimes just after, sometimes right in the middle. Do it 100 days in a row, and your arrivals spread out evenly across a gap. And the average of spread evenly across 10 minutes is exactly half, 5 minutes. So here your intuition is perfect. Hold on to it for a second, because now we're going to take the clockwork away from the bus, and then it falls apart. Because real buses don't run like clockwork. One's stuck in traffic, the next has a clear road. At one stop, 50 people pile in, at the next, nobody. And then something almost cruel happens. Transit planners call it bus bunching. A bus that runs slightly late picks up a few extra waiting passengers at every stop. Boarding takes longer, so it falls even further behind. The bus behind it finds empty stops, catches up, and ends up riding almost on its bumper. The clean rhythm turns into double packs, two buses nearly together, and behind them, one big, yawning hole. And that hole, in a second we'll see, is exactly the stretch of time you're most likely to walk into. The gaps aren't all equal anymore. They vary, and the moment they do, that whole tidy half calculation tips over. Here's the trick our heads just skip right over. The timeline again, but now with uneven gaps. A few narrow 5-minute gaps, a few wide 15-minute gaps, all jumbled together. You arrive at random. Your arrival arrow drops somewhere on the line, every instant equally likely, no moment favored. But look closely at where it lands. The wide gaps take up far more room on the line. A 15-minute gap is 3 times as wide as a 5. So it's also 3 times as likely that your arrow lands inside it. You don't catch some random, evenly picked gap, you preferentially catch the big ones. The short gaps whip past while you're not even there. The long ones, though, they're practically waiting for you, and that's where you get stuck. Your entire waiting life happens inside the big gaps. Let's work it out on a tiny example entirely by hand. Half of all the gaps are 5 minutes long, the other half are 15. The average? 5 plus 15 divided by 2, 10 minutes, exactly like the clockwork bus. On paper, the same bus, the same promise. But now count the time, not the gaps. Out of every quarter hour, 3/4 of it sits inside the big gaps, and only 1/4 inside the small ones. So if you arrive at random, you land in a big gap 75% of the time. Now the waiting time, weighted. In a 15-minute gap, you wait 7.5 minutes on average. In a 5-minute gap, only 2.5. 3/4 times 7.5, 1/4 times 2.5. That comes to 6 minutes 15, not 5. The bus still comes every 10 minutes on average. Not a comma on the schedule has changed, only the gaps vary now, and you foot the bill. The whole thing fits into one sentence. Your expected wait is half the gap plus a surcharge. And that surcharge is the spread of the gaps, a measure of how much they jitter around their average. With clockwork, nothing jitters. The spread is 0, surcharge 0. You're at half, at 5 minutes. In our 5 and 15 example, the spread is just big enough that the surcharge works out to 1 minute 15, and there you are, back at the 6:15 from before. Same number, now straight out of the formula. The moment the gaps drift apart, that surcharge grows with them. The wilder the chaos, the more extra waiting, and it's never negative. Irregularity can only lengthen your wait, never shorten it. A perfectly regular bus is, mathematically, the best possible bus there is. Every bit of disorder above that, you pay for in life spent at the stop. And now comes the moment where this might start to look familiar. The gap you typically experience is the average of the gaps, plus the spread, divided by that average. If you already know the friendship paradox, this is, character for character, the same formula. There, your friends have more friends than you on average, average plus spread over average. Here, your gaps have more minutes than the schedule promises, average plus spread over average. It's the same bias, just wearing different clothes. In the friendship paradox, the popular people show up on especially many friend lists. Here, the big gaps fill up especially much of the time. Big things get oversampled everywhere, with people just as with minutes. One selection rule, sample in proportion to size, and it couldn't care less whether the thing it's sizing up is a person or a stretch of empty time. How far can this surcharge actually go? Let's push the chaos to the limit. Picture buses that arrive completely at random, no schedule, no order, each bus totally independent of the last. Mathematicians call that a Poisson process, the exact opposite of clockwork. This pure randomness has a startling property. It's memoryless. No matter how long you've already been standing at the stop, 5 minutes, 10, 20, it's brutal. The next bus doesn't care one bit. Your expected remaining wait in every single moment is again the full average gap, as if you just walked up. The bus simply doesn't remember that you've been standing there waiting. And that's why, with purely random buses, you wait the full 10 minutes on average, exactly as long as the entire gap between two buses. There it is, the bet from the very beginning, and it's won. Lovely theory. But does it hold at a real stop with real buses? Someone actually checked. A data scientist pulled the real arrival times of the rapid buses in Seattle, a busy downtown station, thousands of log trips, a daytime interval somewhere between 10 and 15 minutes. The result, people there wait measurably longer than half the interval. The paradox is real, not just a thought experiment, but they don't reach the full 10. Real buses aren't completely random, a schedule always tugs them back toward order. The truth sits between the two extremes, closer to 5 for a well-run line, closer to 10 for a chaotic one. The same bias turned up in Boston. The trains on the Red Line run 7.8 minutes apart on average in reality, but riders experience 8.8. So somewhere between your 5 and the full 10. And the less punctual your line, the further you slide toward 10. And with that, the paradox dissolves without a single number ever having lied. Every 10 minutes on average, that's completely true for the schedule, for the buses. From the bus's point of view, everything's in perfect order. But you're not a bus. You're the random arrival, and you experience time length-weighted. The big gaps eat the lion's share of your day, and you miss the small ones almost every time because you're so rarely standing in them. Your average and the schedule's average are simply two different numbers. One counts buses, the other counts you. The average didn't lie to you, you just read it from the wrong side, from the side of the person standing in the middle of the gap, waiting. And the loveliest part, this one bias is everywhere. The same math that makes your bus run late makes your friends look more popular than you, literally the same formula. And it's hiding in your old class schedule too. Ask around, and almost everyone remembers the classes as too crowded, even though the average was small. Big classes simply have more students who remember them. Big things get experienced more often, always, everywhere. Whatever you bump into just by showing up, you bump into the big version of it. So the next time you're standing at the stop thinking, of course it takes forever today, that's not on you, and it's not bad luck, that's on time itself. And there are more stories like this one.